Hi, this is Michael Glasgow here presenting me and Nick Carlin's term project for Dr. Mativo's dynamics class. For our project, we examined the collision between two pucks on a table shuffleboard. For those unfamiliar with table shuffleboard, it is a miniaturized version of the original game. It's played with weighted pucks on a table that is usually waxed and covered with something with small particles like sand, which greatly reduces the friction, so that the pucks can be thrown a lot further with a lot less force. And you can see a picture of it there on the right. Opponents slide the pucks towards the opposite end of the table to score, and the closer you get to the edge of the table without the puck falling off, the more points you score. The goal of this project was to create a collision between two pucks in a game of table shuffleboard that would result in the most points scored for the thrower. Then, through an analysis of this collision, we could determine the best angle and velocity to throw the puck for any game of shuffleboard. Using the calculated velocities, we can then calculate the deceleration of the puck after the collision and use that to calculate the force of friction. And here you can see the setup for our collision. Puck A is sitting in the throwing region of the board, and puck B is sitting right on the border between the 1 and 2 point regions of the board. And puck A will be thrown into puck B so that the resulting collision lands puck B in the 5 point region of the board. Using a recording of the collision, the measurements of the initial and final positions of puck A and puck B with regards to a reference point and the conservation of momentum, we'll be able to determine the velocity of puck A before the collision and the velocity of puck B after the collision. The video you see playing is of the collision that resulted in puck B landing in the 5 point region of the board that we got after a few trials. And here's a picture of pucks A and B after the collision. Now we have a dimension diagram of our collision. If we use puck A's initial position as a reference point, puck B's initial position is 61.5 inches in the x direction and 3 inches in the y direction. After the collision, puck B traveled 23.5 inches in the x direction and 6.9 inches in the y direction. And now Nick is going to discuss our results and conclusions.
Before performing our calculations, we must first set parameters and assumptions which will help us simplify our data. First, we'll assume the velocity of puck A before the collision will be constant, and it's the measured velocity from the video earlier. This will be represented as our V average. Secondly, we'll assume a perfectly inelastic collision. And third, after the collision, we'll assume that the only forces acting on the puck sliding is the friction with the board. Here we have many other measurements that will be used later on to make up for bulk of the calculations. We have the velocity of puck A prior to the collision, measured at 31.04 in inches per second. We got this value by measuring the time it took for the puck to slide across a known distance. In addition to this, we have the travel of puck B and puck A after the collision occurred. And we have the origin point of puck A. Knowing these, we could solve for the angles needed. After the collision of puck A and puck B, we can use the conservation momentum and the final resting place of puck B to solve the velocity transferred from puck A to puck B during the collision. Now knowing the initial velocity, the final velocity, and the distance traveled of puck B after the collision, we could find what its acceleration was due to the board surface. After solving for acceleration, we could use Newton's second law to solve for the magnitude of the forces acting on puck B as it slides to a stop. From our assumptions earlier, we assumed that the frictional force is the only force acting on puck B after the collision occurred. With the entirety of forces acting on puck B being the frictional force, and already knowing the mass of the puck which slid, we solve for the coefficient of friction, which is listed here at 0.05. In conclusion, we are able to use our observational data to solve for the frictional force which occurs between the puck and the board. We could then use this frictional force and apply it to any situation to determine what the optimal toss would be. To visualize this, on a clean table with no other pucks, we can guarantee that the maximum points could be achieved by tossing the puck in a straight line with a velocity of 75.9 inches per second, where you release the puck 146.5 inches from the desired end. Using our calculated values, we can guarantee that this would result in a hanger, which will score the maximum amount of points. Although in that example, we considered a clean, straight throw, The same principles can be applied to any situation. As long as you know the location of the other pucks and the location which you'll throw from, you can use the same calculations that we use to solve ours to solve for the best possible throw. As with any design project, we must address the concerns and the potential errors which may have happened while we solved our problem. First, we must consider the surface which we're sliding on. The sand or the sawdust may not be evenly distributed. This may have resulted in variations in friction from one location to another. Second is that each board may be different in either dimensions or pucks, resulting in minor changes which need to be met through the calculations. For our calculations, they were all based on the board that we used and the weight of the pucks that we were provided. Third is considering the human error. In our calculations, we used video and hand timing to calculate the velocity of the puck as it moved across the table. Considering that human error is a problem, there may be slight variations in the velocity and therefore the frictional forces we solved from it. In addition to this, the measurement of the distance of the pucks traveled after the collision were left to the human eye. We saw in the video that puck A appeared to not move after the collision, even though the conservation of momentum would say it does. And finally, and most important, is that all calculations were based on a single occurrence. More testing may provide more accurate results because of the larger data pool. Overall, there may be slight variations and changes between set to set, but we were able to come up with reasonable, understandable numbers to describe what happened on the board the day we tested and what would happen in the future if done again.